Hi, I'm Chris Wilcox, a software engineer on the Python tools team. And in this video, we're going to explore cross-platform debugging using Python tools for Visual Studio. We'll enable remote debugging using PTVSD, configure the remote machine, and debug Python running on Linux. We have an existing application we're going to use. It's a fairly simple application that I like to call cross-platform debugging. It's really a simple guessing game. You provide your name, it provides a random number between 1 and 20, and you get 6 chances to guess correctly. Along the way, it will hint at you whether you're low or high. If you're successful, it will give you a delightful message. And if you're unsuccessful, it will tell you something a bit more disappointing. Our code is complete, but we want to support future debugging, so we're going to want to add our debugging module. I already have these lines commented out at the top of the file, and so by uncommenting them, it's now in. All these lines do is import a PTVSD module that we provide on the Python package index, and enable attaching to it using a secret key that we specify as xplat_demo. There are other parameters to enable attach, such as specifying the port we're going to use, which for this demo we're using the default of 5678, as well as settings that would allow you to use things such as OpenSSL to secure your transport. While not entirely necessary, you may wish to get PTVSD onto your Windows machine, so that way you have IntelliSense support from Visual Studio. We can go to the Python environments window, go to pip, and from here we can run PTVSD, and you can see it's prompting already for us to install PTVSD. You can also see that I already have PTVSD installed on this machine, so this is unnecessary. So, we now have the setup on Windows. But how do we get it over to our Linux machine? Well, from here we can go over to PuTTY, and we can open the file in Vim. Because this is a single file project, we don't have to do anything more complicated than just paste it into Vim. We also need to take a moment to install the PTVSD dependency. Like most Python packages, we can install it through pip by running sudo pip3 install PTVSD. I'm not going to run this here, as I've already installed it myself. After we've done that, we can run python3 demo.py. And this will run our application over on the Linux VM. It prompts me for my name. And now it asks me to guess. I'm going to guess 10, because I think that's a completely reasonable starting point. Lo and behold, it tells me my guess is too low. I've personally had enough of this guessing. We have this magical thing called a debugger that's about to help me make much better guesses. I'm going to put a breakpoint on line 11, so that way after we've made our guess, it stops. I'm going to attach to the process using Python remote debugging transport, as well as entering in the qualifying area our secret, which we specified as xplat_demo, and the host name, in this case, pythondemo.cloudapp.net. If we refresh, we'll see in the available processes, there's a Python 3 process running on a 64-bit Linux machine. We can now click Attach, go back over to our Linux machine, and make another guess. So my guess was too low. For a second guess, let's do 15. And we're now broken into our code running over on Linux from Python tools for Visual Studio. You can see in the autos window that we have 2 variables that it thinks are interesting to us. Our guess of 15 and the fact that we've made 1 guess. I can step ahead using the Python debug interactive window, my preferred way of exploring a debug process, and now see that guesses made has been evaluated. We can also look for additional things such as my name, and most interestingly in our case, the number. The number was 13. You know, I wasn't getting there anytime soon. And now we know. So from here, we really have 2 steps we can take. We can either go back, continue out of this process, go to Linux, enter in 13, and look like we knew what we were doing. But you know, I can tell from these print messages that it's going to tell me how many guesses I took. And that's going to say that I took 3 guesses to get to a number between 1 and 20. I'm not happy with that. Thanks to the debugger, though, we can fix that. I'm going to go ahead and set number equal to the guess I made. So now we can see if we evaluate that number is now 15, just like guess was. So that's solved. But again, for that whole problem that it's going to think I took too many guesses. Since we're in here, let's have a bit of fun at the computer's expense. I think it'd be great if I somehow came to the conclusion that the number it picked all along was 15 with -1 guesses. So now that we've set that up, I can go ahead and continue the process and be told that I'm amazing at guessing numbers. It says, "Good job, Chris. You guessed my number in -1 guesses." With remote debugging using PTVSD, we can quickly debug a variety of remote applications, all while having the power of Python tools for Visual Studio. Thanks for watching this video. You can get PTVS or watch the other videos in this series from the links below.
Hello, I'm Hugues, a developer on the Python Tools team. PTVS has first-class support for source control systems, such as Git and Team Foundation Server. In this video, we'll connect to a Git repository on GitHub and a TFS repository on Visual Studio Online. First, let's look at using a GitHub repository. I have an existing repository, which is a fork of the Azure SDK for Python. The SDK gives you access to Azure services such as blob storage. We'll click on the clone URL to copy the value to the clipboard. In Visual Studio Team Explorer, select Local Git Repositories and clone. We'll paste the clone URL and click Clone. Visual Studio will download the repository to your machine. Double-click on the repository, and you'll see a list of Visual Studio solutions available. Double-click it to open. Before we make any changes, we'll create a local branch to work in. I like to make related changes locally in a branch, then push the changes from that branch to GitHub. So we'll go to the branches page, click New Branch, we'll create a branch named Blob Test, and we'll select Origin Master, which is the master branch on my GitHub repo. Click Create Branch, and we'll automatically switch to it. At this point, we can start making changes. Let's add a test that shows how to upload an image file to an Azure storage blob. From the test folder in Solution Explorer, select Add New Item. Select Python Unit Test, and we'll call it Test Blob. I'll fix up these auto-generated names. And I'll use a code snippet to insert the desired test code. So first we initialize the blob service with the test credentials. Then we create the container with public access to its blobs. Next, we upload a local image file to a blob in that container. Then we use the request library to download the blob using the public URL. Finally, we verify that the contents of the blob matches the contents of the local file. To run this, we're going to need a file named myimage.png in the data folder, so let's add one to the project by dragging it from Windows Explorer. Let's switch to Test Explorer, which will discover all the tests in our solution. Select the test, blob test upload. We'll say run selected test. And the test passes. Great. Let's review our changes in Team Explorer. So we'll add a commit message. And we'll click commit. We can now sync to push our changes to the GitHub repository. And click sync. Let's review our commit on GitHub. We'll go to the commits page. And sure enough, it's there. If we click on it, we'll see our changes. If we wanted to contribute this change to the official Azure SDK, we could issue a pull request on their repository. Now let's have a look at using Visual Studio Online with TFS source control. We're going to connect to this project, which is a simple number guessing game. Click Open in Visual Studio. This will open in Configure VS with the connection strings to the project on Visual Studio Online. We'll need to configure the workspace to specify where to map the files locally. Click Map and Get. We can use Source Control Explorer to view the contents of the repository. To open the solution, double-click on it in Source Control Explorer or use the shortcut in Team Explorer. I've received reports that although the game works fine on Python 2.7, it doesn't work on Python 3.4. Looks like the author used Python 2.7. Let's add Python 3.4 environment to the project. And we'll activate it. After PTVS reanalyzes the code for Python 3.4, one of the issues is pretty obvious. Print now requires the use of parentheses on Python 3. Let's fix the calls to print. That looks better now. The other issue isn't as obvious. Raw input has been renamed input on Python 3. With these changes, the game will run on both Python 2.7 and 3.4. When files are changed, they are automatically checked out from source control. Solution Explorer indicates that they are checked out with a red check mark. You can get an overview of all the modified files in Team Explorer. You can dig in deeper and compare the contents of the files you've modified with their original version. You'll notice that PTVS even does syntax highlighting in the compare window. After you've tested your changes, enter a comment. And then check in. Back in Visual Studio Online, we'll verify that our commit is now available. Click on Code, and then Change Sets. And we can see our commit here. Thanks for watching. You can get PTVS or watch the other videos in this series from the links below.
Hi, I'm Steve, a developer on the Python Tools team. In this video, we're going to be looking at creating, building, using, and debugging native extension modules in Python Tools for Visual Studio. Now, Python has a bit of a reputation for not being a very fast language, though it makes up for that by saving in developer time. But sometimes you really can't get around needing to improve the performance of your code. Here, I've implemented the hyperbolic tangent function in pure Python code, and a couple of benchmarks to test how long it takes to process a list of values. When I run them, we'll see that it really doesn't make much difference whether I use a list comprehension or the append function. It's going to be pretty slow, and that's because of the tanh function. For this particular case, I should really just be using the math module or a library like NumPy, but this could be any function that's in your innermost loop, and sometimes you really don't have a choice but to write something in C. Luckily, Visual Studio supports multiple languages, including C and C++, which makes it easy to build an extension module. We'll start by adding a new empty C++ project. We'll call it Superfast Code, because it will be. And I'm going to add in an existing file for the demo, which is based on some of the Python samples. So it's a simple module with one function. You'll see there's errors everywhere. We can't actually build this without updating some properties on our project. First, we need to set the target name to make sure it matches what our module is going to be called. This is very important for Python to be able to import it. The target extension should be PYD. Configuration type has got to be dynamic library. Under C++, I'm going to provide my Python include directory as an additional include directory. I'm using Python 3.4 for this. In the preprocessor, I will set the PyLimited API preprocessor definition. This restricts some of the functions that I can call from Python, but at the same time it will make my code more portable between versions of Python 3 and allow me to use sometimes incompatible compilers to compile my extension. Finally, in code generation, I want to select multi-threaded DLL as my runtime library. And under linker, I have an additional library directory, which is my C, Python, libs folder. Now most of the errors are gone, except for this one about the tanh function, which is not defined. So to implement that, I'm going to come back to my pure Python code and copy it in, and we'll just simply port it over. This is fairly straightforward because it only uses primitive types. The tanh function is going to use some PyObject parameters so that we can directly interface with Python code. You can find more information about these in the Python documentation. Now my project builds, and I can come back to the Python code, add a reference to the project, and then immediately come down here, and from Superfast Code I can import my new fastTanh function and add a benchmark for that. Now when I run this code, we'll see that even though the two slow benchmarks with pure Python code are there, simply changing it to be C code has dramatically reduced the amount of time this operation takes. But what about when things don't work properly? Here, I have a far more complicated project which has a lot of calls back and forth between Python and C, but when I run it, we get a type error And according to Python, there's an integer required, but according to the stack trace, it's coming from this format function, which actually has nothing wrong with it. Clearly, the error must be deeper in the C part of my code. Normally, I'd set a breakpoint and start stepping through so I can see what isn't working quite right. And with Python tools for Visual Studio, this is actually still the case, even though half of our code is in Python and the other half is in C. Here's how you can do it. First, on our Python project, we have a debug property to enable native code debugging. If you don't select this, we'll treat it as pure Python code and you won't be able to see your C code. And now I can hit start, and we see an error pop up because to do mixed mode debugging, as it's called, you require the symbol files for the Python interpreter that you're using. This button will take you to a web page that will help you find the right symbols, and once you've copied those onto your machine, you can simply come here and add the path containing those symbols to your symbol path. Now when I start debugging, it will work correctly, or it won't work correctly, and we'll roll back and try it again. Now when I start debugging, it will work correctly and will hit the breakpoint, and I can start stepping. And when I step into a function that's implemented in C, you'll see that we're suddenly in C++ code and stepping through that. When I reach a point that calls back into the Python code, we'll jump back into the Python file. And you can see in the call stack that we have both languages available and can switch between the calls wherever I like. At each point, you can hover over variables and inspect them, and it will show you a Python view containing whatever properties or members we know about for the Python objects. And as usual, the autos window will work as well as locals. And these work identically in the Python code or in the C++ code. But stepping is not actually going to help me find my problem here, because there's a lot of code going on. Luckily, there's an easier way. What I really want to do is stop running as soon as the exception is set, whether it's in C code or in Python code. I can do this with the exceptions window. Debug, exceptions, and now I want to browse through Python exceptions to find type error, which is the exception that we're seeing. I can enable braking when that's thrown, and hit continue, and we immediately stop running at the point where the exception is set. We can see here that this is a conversion from a string trying to convert to an integer, which is failing, but we don't actually care about the result of this, so it's very easy to stop running, make the change. I need to ignore that exception, and now when I rerun the program, it will rebuild, and we've completed successfully. Working with Python native extension modules is not always easy, but in this video we've seen how Python tools for Visual Studio goes a long way to help you build, test, and debug C extensions. Thanks for watching, and you can get Python tools for Visual Studio or watch our other videos from the links below.
Hello, I'm Dino Wieland, a developer on the Python Tools team, and in this video I'm going to show you how to create a Django website, configure MySQL on Azure, and deploy the website to Azure websites. So first I'll start off by creating a new project. I'll select File, and then New Project, and you can see that I have a number of Python options to choose from. Because I've installed the Python samples package, I also have these additional samples available, and so I'll select the Pols Django web project. Click OK, and the project will start being created. I get our standard prompt to install either into a virtual environment or install into Python 3.4 or follow up and install the packages by myself. And I'll just go ahead and create a new virtual environment and install the packages into that. I can give the virtual environment a name and choose a base Python version to install from. I'll just accept the defaults here. Next, I need to synchronize my database. I get instructions on screen here that are pretty helpful that tell me exactly what I need to do. So I'll open Solution Explorer here, and I will right-click on my project. There's a nice Python menu. Under that is Django SyncDB, which I'll select. This brings up the Python interactive window where I see the Django SyncDB command is running. So I'll just go through the prompts here. And use a super secure password. And now I've completed the Django SyncDB. At this point, I can run the app. So I'll just click on the play button, or I could press F5. And the app will launch along with my web browser. Here you can see I'm in the default app. I can click Create Sample Polls, log in with the account I created before. So I can vote on the polls now. And you can see the basic app is now running and working. Next, I'm going to create a MySQL database on Windows Azure. So first, I'll go to the Windows Azure Management Portal and sign in. So here I am in the Microsoft Azure portal, and in the bottom left-hand corner you can see the New button. I'll click on New and select Marketplace, and this lets me select a number of different applications and services that are available. I'm just going to scroll down to ClearDB MySQL Database, click Next, select Free, and give this a name. Click Next. And confirm my free purchase. Once my database is created, I can click on Connection Info to get my connection strings. Next, I'm going to switch back to PTVS, where I'm going to install the MySQL client. So here I have my virtual environment, and I can right-click on it and choose Install Python Package. I'll just type in MySQL Client and click OK, and this will use pip to install MySQL. Once the package is installed, I can go to my settings.py file and configure my database to use it. So at this point, I'm going to copy my connection string into my settings.py file. I'll pull the entire connection string over here and take the database name and put it in the name field. Take the machine name and put it in host. Take the user ID and put it there, and the password. Finally, I'll change the engine to be MySQL. Now I can go back to Solution Explorer, right-click on my project again, choose Python, and rerun Django SyncDB. You can see it runs again, but this time it's running against the database that's hosted in the cloud. Once again, I answer a few questions. Give my super secure password. And the SyncDB is done. Now I can run again I'll hit F5, which will again launch it on my local system and bring up the browser. You can see, once again, we have no polls available because we're running against a new database. So I'll create the sample polls, logging in to do so. Once the sample polls are created, I can answer them. And you can see that my app is now working, but this time talking to the database in the cloud. So finally, I'm going to take my application and deploy it to Windows Azure websites. So I'll right-click on my project again and choose Publish. Choose Microsoft Azure Websites. And choose to create a new website. I'll select a region and click Create. Now I just need to press Publish. Here you can see in the bottom left-hand corner that the publish has started, and all of my files are being collected from my project and my virtual environment and will be deployed to Windows Azure websites. Once the deployment is completed, my browser will open and we can see that I'll be running on the cloud. So here you can see I've launched my browser and the URL is at azurewebsites.net now. But my questions are still here and I don't have to pre-create the sample questions this time because we're running against the same database as we did when we ran locally. So here I can go in and vote again, and we can also see my previous votes are there as well. Thanks for watching. You can get PTVS or watch the other videos in this series from the links below.
Hi, my name is Pavel Minaev, a software engineer on the Python Tools for Visual Studio team. In this video, we are going to talk about switching between different Python interpreters, installing and removing packages, and creating and using virtual environments. There is more than one implementation of Python available, and Python Tools not only supports all the most popular ones, but also allows you to conveniently manage several implementations installed side by side and easily switch between them for your different projects. In Python Tools, different implementations or different installations of the same implementations are referred to as environments. Strictly speaking, a Python environment is a combination of a Python interpreter, an associated standard library, and any other packages that came pre-installed or were installed into that environment later. Let's open the Python environments window. It's under View, Other Windows, Python Environments. As you can see, I have 4 different implementations here. The bottom 2 are entries for a 32-bit and 64-bit versions of the reference Python implementation, also known as CPython. And the other 2 are for IronPython, a different implementation that runs on top of CLR and the .NET framework. The first thing we need to do is to create a completion database for the environment that we're going to use. This covers all the standard modules and pre-installed packages that came with it and is used by IntelliSense, refactoring, code navigation, and other code-centric features. Until the completion DB is fully created, those features will be limited or unavailable. This is indicated by the warning icon that appears in the Environments window next to the new environment. To start the process, I switch to the IntelliSense tab and click Refresh DB. We can observe the progress here as well.
For large Python installations with a lot of packages, it can take several minutes to complete, but a bare bones CPython install should finish it pretty quick. Since we have more than one environment, there is a question of which one will be used by Python tools. There are several points at which this can be defined. First of all, there is the notion of the active global environment. This is the one that has its name displayed in bold in the list. So right now, that's Python 3.4. I can easily change it to IronPython, like this. And then I can change it back in a similar way. The active global environment will be used for all projects unless the project explicitly specifies a different one. Let's see how that works. I'm opening a simple console application project, which will print out the version of Python that it's running on. If I open the Solution Explorer, you can see that under the project node there is a child Python environment nodes, which also displays environments, similar to the environments window. However, it only has a single node under it, indicating that this project just uses the default global environment, which is Python 3.4. If I run it, I can see the version string corresponding to it printed out. Let's have a quick look at the editing experience as well. Note how when I type import, I get the list of available modules and packages. This list is coming from the completion database for this particular environment. And we can see that there are modules here, like async.io, that are only available in Python 3.4. Clicking on Add Remove Environments commands on the Python Environments node allows me to change the environments in this list. Note that I can select more than one entry here. Let's select both IronPython and Python 3.4 and see what this looks like now. Now the node in Solution Explorer shows both of my selected environments, and once again, one of them is bold, indicating that it is currently active. Unlike the environments window, however, what you see in Solution Explorer is specific to this particular project. So the active environment is the one that this project will run under and does not affect other projects. Again, this can be easily changed via the context menu. If I go to the editor again and try to import something else now, we can see that the completion list is different. Async.io is gone, and we can see other packages such as CLR now, indicating that this comes from IronPython. I can also import .NET namespace such as system. And if I try to run this program again, we can see that it prints the version number accordingly. I have mentioned before that Python environments always come with the standard library, and sometimes also with some pre-installed packages, but that they can also have packages installed into them afterwards. Let's see how this is done. Python packages are normally installed using the standard Python package manager that is called pip, a recursive acronym for pip installs packages. The primary repository for packages is PyP, the Python package index, and this is what pip uses by default. PyP has a website where the packages can be listed and searched, but PDVS provides an integrated experience for that directly inside Visual Studio. In the Environments window, switching to the pip tab shows the package management UI for that environment. As you can see, it already has some packages installed, which are pip itself, and setup tools, which is the dependency of pip. If I type something in the search field, for example, Azure, I'll get a list of relevant PyP packages, and I can select one to install. Let's install the official Azure SDK package. This is the one that's simply named Azure. Installation log is displayed in the output window. Looking at it, we can see that it also installed some other packages, which were dependencies of the Azure package. If I clear the search box now, we can see all the installed packages in the list. Now that the packages are installed, Python tools will go ahead and automatically refresh the completion database for this environment so that classes and functions in those new packages show up in IntelliSense. And we can see the progress bar in the Python environments window. As you can see, it already has some packages installed, which is pip itself, and setup tools, which is its dependency. Setup tools has a new version available on PyPy, which we can install by clicking on the upgrade button. If I type something in the search field, for example Azure, I'll get a list of relevant PyPy packages and can select the one to install. Let's install the official Azure SDK package. That's the one that's named simply Azure. Installation log is displayed in the output window. Looking at it, we can see that it also installed some other packages that were dependencies of the Azure package. If I clear the search box, we can see them in the list. Now that packages are installed, PTVS will go ahead and automatically refresh the completion DB for the environment. So the classes and functions in those new packages show up in IntelliSense. Packages can also be removed by clicking on the Remove button. For example, we can remove Azure. Note that this didn't remove any dependencies of the removed package. So far, we have installed packages into the global environment, and so they were available to all projects that are used in that environment. This may seem convenient, but you can only install a single version of the package globally at the same time, and sometimes you want to manage package versions specifically for a given project. To solve this problem, Python provides virtual environments. A virtual environment is a Python environment that shares the interpreter and the standard library with some global environment, but has its own set of user-installed packages, which is separate and isolated from either that global environment or any other virtual environment. Thus, every virtual environment can have its own version of the package installed into it. It's convenient to think of virtual environments as tied to a specific project, and PTVS workflow is centered on that notion. An environment can be created for a project via the Environments node in Solution Explorer. The name serves only to distinguish the environments from one another if you have more than one in a project. You can also specify some global environment to serve as a base. IronPython does not support virtual environments, so let's select Python 3.4 as a base and go ahead. The environment has been created, and the basic set of packages to manage it is installed using pip, with progress displayed in the output window as usual. You can also see it appear under the Environments node in Solution Explorer, where the name of the base environment is displayed alongside, and also in the Environments window. Note how the environment has its own completion database. This is due to the fact that it can have a different set of packages from its base environment. Once created, the virtual environment behaves very much like a global environment. We can make it active for this project and install packages into it. Let's install Azure again and verify that the package is contained in the environment to which it was installed. As you can see, the package shows up in the virtual environment but does not show up in its base environment. For all the convenience that virtual environments offer, they have one flaw. They cannot be easily redistributed or even moved around because their path is hard-coded inside them. So if you want to move your project to a different machine or share it with someone else, you have to provide them with a list of packages which can be used to recreate the same environment again. Python Tools provides a convenient way to do just that. The list of packages is conventionally placed in a separate file in the project named requirements.txt, with one package name per line. In the context menu for the virtual environment, there is a command that will automatically generate that file based on the current set of packages. As you can see, the environment is completely restored to its original state. So what happens if I have a generated requirements.txt and then I add more packages? Suppose I install another package. Let's install requests. The new package does not automatically show up in the requirements.txt file. But if I try to manually regenerate the file again, I can see that I get various options on how to handle the changes, whether to regenerate the file entirely or to add new entries to it or update any versions of any packages that were already in the list. Let's try creating another virtual environment now. As you can see, when creating a new virtual environment, if the project already contains requirements.txt, its contents will be used to populate the newly created environment by default. Thank you for watching this video. You can watch other videos in this series covering other Python tools features or download the product itself at the links below.